All right. Good morning, everyone. Um, I guess the recording has started, and let's kick off. So this just for 90 minutes, and it's an introduction to a 6-part series of what will be, you know, on fundamentals of industrial automation, right? Essentially, what I have set out to do is to build intuitions, right? First, build intuition. Secondly, build a solid base for understanding what this thing we call control system is, right? So for some of you on the call, this might sound elementary, but I know that there are students also on the course that are doing taking control system courses, right? And of course, most of you that did electrical electronics, you know how far the thought or the teaching was from reality. So my goal is to bridge that gap, and we're going to start with almost zero mathematics, right? We will eventually get to the mathematics for those that are interested. And when I say the mathematics again, the mathematics will not be such that it will help you to pass exam, but it will be such that it helps you to fully understand what is happening inside the control system's black box. All right. When you have that understanding, whatever maths you get taught at school or whatever application you need to face, all right, it will be very easy for you to navigate through it. This session, this series covers 6 different sessions, all right? And I deliberately broke it down like that. Definitely we'll do it every 2 weeks. And if possible, maybe weeks where I have time, we can even do it every week in order to quickly cover this. After this, we'll now be able to drill down into the practical questions on the field. My view on control systems and automation training has always been that one must approach the training from a vendor neutral point of view. That is, if your goal, your long-term goal is to be a specialist, a control system specialist, you need to first understand the system in a vendor neutral manner, such that Siemens, Rockwell, Schneider, Emerson, Foxborough, Yokogawa, and all of those things are not shaping your thoughts. Your thoughts should be shaped by what the logic behind control system, the thinking behind it, the paradigm, the mindset. So in this session, in this series rather, we'll be looking at why feedback exists. And that is what we're dealing with today. The next one will be inside the loop. That is when we'll now drill down into the control loop itself, right? That's when we'll look at the sensors, the actuators, the processes, right? And then why loops fail silently. Because at the end of the day, loops are the building block of control systems, right? In a typical plant, you can have as much as 50,000 loops, control loops. So it's just loops are just like cells in the human body. When we say that a cell is Okay, my biology is correct. Okay, let's just assume that everybody knows what cell is. I can't even articulate it, right? But a cell is the smallest division or unit of human life or whatever, and that's exactly what loops are in control systems. So section 3 will now go into the dynamics, and that is when we begin to introduce the mathematics gradually. We look at the first order and the second order behavior. We'll treat the plant as a personality, right? And then we'll look at the first order, and then we'll look at the second order, as in those dynamics that affect the plants. And this is where even the experienced guys will find this very useful, especially those that want to write exams such as the CAP or CCST and all of those things, right? And that's why if you're here today, right, let me speak like a pastor. You are very lucky, or how do they say it? God brought you here, that's the hype, right? But if you're here today, the point is you need to try to follow through from session 1 to session 6. It's going to liberate, it's going to open up your understanding, and it's going to really build a solid foundation upon which you develop your career. And for those that are already experienced, right, it will fill in some pockets of air in your knowledge gaps. It will fill it in. So that's session 3. Session 4, we will now look at controllers. We will demystify controllers. That is when we look at the classical control theory, the proportional controller, the PI controller, and the PID controller. We'll look at their behaviors. We'll look at a bit of mathematics. We'll look at tuning, right? And so our perspectives will be from logic thinking, because we're actually trying to control physical processes, right? Then section 5 will now focus on what I call from whiteboard to the plants, right? And we'll now be looking at proper process. Look at well heads, look at separators, we'll look at motors, right? We'll look at pumps, we'll look at manufacturing processes, we'll look at pharmaceutical processes, right? Food processes. And then section 6 will go into tuning and commissioning, right? Essentially, we'll be answering the questions why most control problems are design problems in disguise, right? So that's what the series is about. Of course, as usual, I'm going to share, this recording will be uploaded into a YouTube channel and shared with you. These slides also will be shared, right? And I'm going to start a boot camp, right? There's going to be a boot camp starting from, I think the last week of this month or the last week of this month or early March, right? And that boot camp essentially is going to focus on these 6 sessions on this series, right? And it's going to cost 30,000 naira, right? And the difference between that and this is that it's going to be a very small and closed group, maximum of 20, right? And it's the difference between that boot camp and this is there will be tasks, there will be assignments, and there will be feedbacks, right? Such that at the end of the boot camp, the participants will have been able to design a small plant, right? Identify all the controls, identify all the possible challenges, essentially go through concepts, conceptual studies up to commissioning on paper, right? Everything is going to be purely online, right? But there's going to be a lot of written work, weekly assignments, and um, all of those things. So, like I mentioned, it's going to cost 30,000 naira, right? And it's going to be a maximum of 20 persons, right? So, if you are interested in it, reach out to Orelua, right? And once we have 20, we'll close it and then probably plan for the subsequent ones. And so essentially, people that will participate will need to allocate time, right? There will be no excuse on, hey, I cannot attend, I cannot do this or not, right? Okay, let me keep that for now. But if you are interested in it, you reach out to Lua and then she will give further details on that. Okay, so let's get into the program for the day. Feedback control and why it exists. This is the foundations of industrial automation. And my name still remains Dapo Shosonya, CAP. I love the title. Okay, so the control systems evolution. Please confirm you can still hear me. Okay, great. So you can drop, as we progress.
Yes, we can hear you.
Okay, great. As we progress, you can drop your questions in the chat. Um, so don't forget. And there will be room for discussion. We will leave here by 10 on the dot, on or before 10. So control systems evolution, uh, we moved from manual adjustments, right? Where operators, we had humans in the loop, where operators, essentially the kind of processes we carry out in the kitchen, in our kitchens at home. When you want to cook, you are the one that carries each of the items, you put them into the pot, which is equivalent to the vessel we use in the manufacturing plants. And then at some point, your mind tells you, oh, you need to stir this. Oh, you look at the temperature. Oh, it is burning. I need to add water. So it is the human agent that is interacting with the vessel, doing all those manual adjustments. In that instance, your brain is a controller and your hands are the actuators. And the process is what you are making inside the pot. The meat, the oil, the water, and all of those things, right? Then we moved into early devices. And that is where the development of early open loop control devices, which allowed for automated processes. That is, using the kitchen analogy again, we just pack everything, the salt, the water, and everything. We just put it there and then we left it. We didn't taste the soup to check whether the taste is as we desired or whether the salt was enough, So that is open loop. In closed loop, you taste and either add a bit, then you taste again, you add a bit. That is, you correct for your error. So from early devices, we moved into the feedback theory era, where, I mean, that was the era that revolutionized control systems, by formalizing the process of measuring. We measure the outputs. That is, you measure the salt. You measure, so you measure the inputs and then measure the outputs. And then you adjust the input again in order to, once you measure the input and output, you look for the difference, you calculate the difference, and then you adjust the inputs in order to correct for that difference, right? So that improves significantly stability and response to disturbances, right? And then we now have the modern PLCs. The advent of modern programmable logic controllers combined with drive technology has created sophisticated control systems capable of real-time adjustments, enhancing automation and operational efficiency in industry settings. And that's it's one of the greatest miracles in control systems, the PLCs, the electronic controller, right? The need for control. Machines don't behave consistently. Every time the load changes, the behavior of the machine will change. Every time the process changes, the machines will change. The process conditions are dynamic. When we say something is dynamic, it means that it is changing, it is moving, right? That is why in control systems, when we begin to do the analysis, you begin to hear dynamic response, right? So disturbances are unavoidable. And because of disturbances, open loop control are not efficient. Disturbances are a given in any process. The weather will change, the quality of your raw materials will change, right? So many things will change. Equipment will malfunction. And once they malfunction, they will introduce a dynamic into the process. So imagine the process of manufacturing soap, and you need to mix caustic soda, perfume, and water. Let's assume those three. You need to mix them together in a vessel in order to produce a specific brand of soap. Let's say, can someone tell me a popular soap brand? Bathing soap.
Premier Cool.
You said?
Eva soap.
Eva. Okay, yeah, Eva. Right. Yeah. I use Eva too. I use it for my skincare routine. So everybody knows Eva, right? When you pick up Eva on the store shelf, you expect a certain level of perfume. You want to smell a certain level of it's not aroma is used for food. Odor is used negatively. I'm trying to find the right word.
Fragrance.
Right. Fragrance. Thank you. So you expect a certain level of fragrance. If you don't find that fragrance, you begin to have doubt in your mind about that product, that this might be fake. You expect it to have to weigh, even subjectively, you put it in your hand and you have a sense of its weight, right? And then even the shape. So now assuming that during the process of production, the flow meter that delivers the perfume into the tank malfunctions or it goes off range. So instead of delivering 10 liters of perfume into that batch, it delivered just 5 liters of perfume. And let's assume that that batch will produce maybe 20,000 bars of soap. Automatically, if you did not detect that error from the flow meter, right, guess what will happen? Most of those batch, that 50,000 bars of soap will probably result in a loss in fact, it will most likely result in a loss for the company because there is a brand identity that has already been associated with Eva in the minds of customers. So when they expected 10 liters of perfume to give a certain level of fragrance, and they found 5 liters giving another level of fragrance they weren't used to, they will just pass by it and pick the next soap and say, this one is fake, right? So those are the things that causes a lack of uniformity in product creation, right? So open loop assumptions. In an open loop system, we apply inputs with expectation of predictable outputs. So for that soap, excuse me, for that soap example, we have our input. We've checked all the instruments before we started the batch processing, right? We checked the temperature meter, temperature sensor, the flow sensor, the valves, the pumps, and everything. We checked everything. Everything checks out, right? And then we supplied all the inputs. And during maybe between, so we started at time 0. By time t plus 5, the flow meter developed that problem, right? But because we are operating an open loop, we did not catch it. So the process will just continue like that and conclude. And once the process is finished and you have the product, you will now realize that, oh, the product did not meet specification. And then it results in a waste. The plant manager gets fired, or the supervisor in that shift gets fired, or whatever. I mean, gets punished. So open loop ignores disturbance. It just assumes that everything is going on well. No checks, no nothing, as it was in the beginning. So, I mean, it continued, right? So in this series, we'll be looking at 2 case studies. We'll be looking at a conveyor system, right, that has a motor, a gear system, and a VFD to drive a conveyor. The conveyor has been designed to carry X amount of load, right? And we'll look at all the possible disturbances, right, on it. We'll look at all the sensors. We'll look at how they are configured, and and how everything interacts, to form a loop. We'll identify the number of loops that we need to have on such a conveyor system, right? So that's one of the case study. The second case study will be an oil production system that moves from the wellhead into a test separator. And we'll look at the process from managing pressure on the wellhead through the pipeline and then into the process tank itself. For this to we'll be using a simulator, right, to help us in understanding those processes in depth. All right. So this case study illustrates how a motor and gearbox driving a conveyor at fixed VFD speed leads to speed droop due to varying load. Terms like droop, we will understand it, right? And resulting in inconsistent spacing and frequent jams, right? And then the test separator, we'll be using a two-phase test separator, experiences challenges due to fluctuating inlet flow. The flow into the test separator is a natural flow. That is, it has minimal control, right? Because it's coming from the reservoir, right? The reservoir beneath the arch cross, and it comes at varying pressure and all of those things. And we do our best to provide some controls at the wellhead, but because of commingling and all of those things, so that inlet into the test separator, and then we need to separate the crude from the oil, and then the gas. We need to separate the oil from the crude. Also, we need to separate the gas from the crude, and then we need to take out the water, because the crude comes in 3 components plus sand, right? We take out the oil, we take out the water, we take out the gas, and then the water, because of regulation, we purify it back to a certain extent, and then in a controlled manner, discharge it, return it to the environment. Right. So those scenarios we'll be looking at. So we've discussed this earlier. Humans as early controllers. Just picture that person in the kitchen, doing all of those tasks, using the brain, using the hand. Even you in the bedroom, if you want to use hot water or warm water for your bath, you step back a bit, switch on the knob or the valve, and then it discharges cold water initially, and then gradually it becomes hot. Then you adjust the knob while feeling with your skin in order to gauge the right temperature. Same thing applies when you drive, right? You press the accelerator, and then you look at the speedometer, and you feel, oh, I'm going too high, I'm going too low, it's safe or unsafe, and all of those things, right? It is these days that we now have vehicles that are fully automatic, that they don't even need humans in the loop anymore. They know when to speed up, they know when to slow, they know the maximum speed to go. They understand the legal speed requirements of the road. They know how to give priority to humans and avoid humans so that they don't crush them on the road. Humans are not structured as machines, and all of those things. So we had humans as early controllers. And technically we'll explain what open loop and closed loop is, right? So open loop control systems operate without feedback, leading to predictable failures when disturbances occur in the process, making them unsuitable for dynamic environments. Dynamic environments are environments where things change frequently. Whether frequently or not, so far there are changes. Those are dynamic environments. And then the closed loop systems, they utilize feedback to adjust operations, enabling them to adapt to changes and maintain consistent performance, effectively managing disturbances and enhancing overall reliability. right? And that's what closed loop systems are, right? And we'll unpack this as we progress. So essentially, purpose of feedback control is for consistency and automation. All right. It is crucial because it compensates for disturbances. So you can begin to see that one of the terms you need to be very comfortable about is disturbances. In this business, there will be disturbances, right? And the essence of feedback is for you to compensate for it. You cannot eliminate disturbances, but you can reduce it to the barest minimum so that you attain a defined stability. Your defined stability could be maybe X value plus or minus 3%, plus or minus 4%, plus or minus 5%, or whatever value you want it to be. So your stability will be within a range that even when disturbances occur, I don't want to drift outside this particular range, right? And then it optimizes process performance. It minimizes manual intervention, and it serves as a foundation for advanced automation systems in industrial environments. So you will agree with me that the concept of feedback is very, very important, and that's why we're devoting a whole session for this. We will drill in more details, devote more time for this in the class, right? But this is the foundation for, of course, the classical control theory, which is a proportional, integral, and derivative, right, acts as a foundation for advanced control theories. When you talk of feed forward, right? Feed forward, it's not separate from feedback. The feed forward control was built on the feedback control. So essentially, feed forward is just an enhancement of feedback, right? MPC, multivariable process control, also utilizes the feedback control. Statistical process control, cascade control, ratio control, all of these things, they built on the feedback control. So that's why if you don't have this understanding, if you just go, oh, okay, I want to learn how to program a PLC, I want to learn how to build a SCADA system, I want to build HMI and all of those things, you will attain functionality in specific instances. But the specialty knowledge that will enable you as a control systems engineer or automation professional to function within any control space will be lacking. And we say, oh, they use cement in my company. That's what I want to learn. And that's very important. Your first priority will be to understand what is happening in your company, the equipment they use and everything. All right. But then you don't stop at that. You drill deeper. And my preference has been that let me stay at the non-vendor level, right? Once you have that knowledge, a non-vendor aligned knowledge, you'll be able to apply that knowledge to whatever vendor, right? I've been fortunate to work directly with two major OEMs, global OEMs, and indirectly with another two. So I've seen systems across all of these OEMs, And I mean, you can boil down their offering because all of them, again, they subscribe to the same standard, industry standard. And that should tell you something. Their systems are similar. But now they have customized systems. So it is customization that separates Rockwell from Schneider, from Emerson, from Yokogawa, from Foxborough, and all of those things, and all of those OEMs. It is customization, the level of functionality each of them have packed in a particular model of their equipment, right? So that's why feedback is very, very important, right? It's crucial because it compensates for disturbances, optimizes process performance, and then minimize manual intervention. Once you have feedback, then you can truly step away from the process, because instead of you being the one checking, evaluating, checking whether the salt is sufficient or not, it is a process, the feedback system that will check, report, and then correct. Check, report, correct, and so on and so forth. So the feedback control core idea, you measure the outputs, you compare the set points, right? And then you make your adjustments. So in a closed loop conveyor control, an encoder measures the actual speed of the conveyor system, allowing the controller to adjust the VFD reference inputs, ensuring stable operation despite varying load conditions and enhancing overall process efficiency. An encoder is essentially a sensor. Apologies for this funny image I used. In actual fact, the actual slide I prepared, I don't know what happened to it. It was when I got up this morning to review the slides, and I realized I couldn't find it. So I had to quickly, build this one just this morning. So I generated that image from, I used AI, but AI introduced some language I don't understand. Let me ask this question. In this instance, who is dumb? Is it AI or the person that gave the prompts to AI?
I think the person that gave the prompt to AI.
Okay, you say I'm dumb, right?
No, you cannot say that because you don't know what kind of prompts he used.
So
Well, I would say, I would say the
I know
whatever
you are trying to say it gently.
outputs, whatever
Go for it.
outputs AI gives depends on whatever it decodes from the prompt given to it.
Thank
So
you,
I
thank
wouldn't
you.
say anyone is dumb.
Okay, you're not saying anyone is dumb, right? But you are saying that the results reflect on, it's a reflection of the intelligence of the person that wrote the prompt, right? Thank you, thank you, thank
Ah,
you.
I don't really agree with that.
Okay. Well, I mean, so at the end of the day, right, the better your prompt, the better the output, right? I actually did not put the prompt in detail. No, that's why AI will place the electric motor on the conveyor. I just gave a general description, when you're doing your prompting, right, you tell it where to put the electric motor, that it should not be, or the electric motor and the gear system, they are controlling the conveyor, which will carry the product. The encoder and the proximity switches and so on and so forth are attached sensors, to the conveyor. I mean, all those details, and it will produce a better image. Well, thank you for the gentle way you gave me the feedback. All right. So the core idea for the feedback control is your outputs, you compare your set points, and you correct the error. So what is the source of set points? Where do we get set points from? Or who issues set points?
The operator.
The operator.
Or the process owner. Yeah.
Or the process owner, yeah. So essentially, it is the human that will determine what the set point is. So that is the instruction you give to the control system and say that I want this control, this system, or this process to stay at this set point, right? And then the feedback controller will take a measurement and then compare that measurement to that set point. And then it will understand the deviation from that set point. Once it understands the deviation from that set point, it now makes a decision. Do I need to increase the input or reduce the input in order to correct this deviation? Right? So that's essentially what the feedback control process is. It reduces the sensitivity to disturbance. And it takes this action continuously, and that is what we call the scan time, right? It goes through it continuously. So if your scan time, I mean, just for the purpose of explanation, is 10 minutes, of course, 10 minutes is not practical. But if your scan time is 10 minutes, that means that you will have disturbances accumulated for 10 minutes before you make correction. But typical control scan time are measured in milliseconds, depending on how precise you want your operations to be. So before the human, if your scan time is in milliseconds, before the human even discovers that a problem or a disturbance has occurred, the system will have discovered it and made a correction for it. And then the human will just sit in front of a screen and say that, okay, this process is doing very well, doing very well, and your products are coming out according to specification. Right. So for closed loop conveyor speed control, you have the encoder will measure the actual speed. The controller will adjust the VFD reference. I hope you understand what VFD is. VFD is the variable frequency drive, right? And that is what controls the electric motor, that moves the conveyor. So in that mechanism, we have the VFD, we have the motor, we have the gear system, right? And then before you begin to see all those movements on the conveyor, right? So the internal torque and the current loops are hidden. And the result is you have stable speed despite load changes. So whether the conveyor is carrying 1 ton of materials or 20 kg of materials, you will see the speed will be stable. Without that encoder making measurements and without the VFD giving reference to the motor, the process will be like a human running uphill. At the base of the hill, your speed will be high, assuming constant energy now. At the base of the hill, your speed will be high, but as you climb, you will see that your speed will naturally decline. All right, as you climb, you begin to slow down. But if there is an automatic input of energy and something that is measuring it, you would see that as you are going up the slope, more energy will be infused in you, and then your speed will remain constant as you go up. So that's what that feedback does. And then in the separator, you have the level transmitter, which measures liquid level, and then the controller adjusts outlet valve, and then the inlet disturbance will be absorbed. Absorbed. So because you are, let's assume that level is your main purpose, right? You are monitoring the level because you don't want that tank to overfill, all right? You monitor the level, and then the controller will adjust the valve based on the level and based on your set point, so that the level in the tank will be kept constant. So process dynamics. Processes have personality, right? Conveyor speed, fast response is required. Separator level, slow response is okay. And this is where we begin to need to look at certain terms. And we're going to still break it down. All of these, we use them in what we call process modeling, right? Time constant, the delay, the inertia. All right, you will see different names for inertia. You will see it presented in different, from different perspectives. All right, when you talk about hysteresis, when you talk about stiction in valves, for example, we have forms of inertia, right? And then the time constant and the delay. We use these terms in process modeling, right? And it also helps even in understanding a running plant, right? How all those equipments behaves. And these are the things that influences or that event that determines your scan time, right? When you write your program. So you begin to see that it's not just even enough to be able to string the logic together, right? You need to be able to string the logic together in such a way that you will cover X amount of lines in a particular scan. So your timing is important. Your timing is important, you know. So we talk about the rise time, the overshoot, and the settling time, right? So a step response is like a unit. So when there is a unit change in the process condition, right, you have a step response to it, right? And it tells us the rise time, the overshoot, and the settling time. All these terms, just hold it. We're going to come to it when we begin to analyze our PID controller, right? At the end of the day, most tuning problems are shape problems, right? You can have in your tuning, I mean, your process can so for example now, you're supplying water into a tank, right? You can design your process such that the changes, maybe you're supplying water from a, let's say, 10-inch pipe, right? And then you have a valve governing the flow of that water, right? And you have closed the valve up to 80%. That is, you allow water to flow 20% of the pipe. And then if you suddenly open that valve 100%, you will see a sharp rise in your graph. You see a sharp rise in your valve, sorry, in your graph, all right? And that is a step response. So you can now design that. I mean, this is now based on the kind of process you are designing or you are running, right? Can you accommodate such sharp response what does it serve you? Or even if failure occurs and the valve fails and it fails open, that is, it moves from 20% to 100%, how does it impact on your product? So all of these questions are questions we'll be answering down the line, right? So, and you see the feedback logic there. Error equals to set point minus your measured value. And then your control output will be equals to control output plus gain times error. What is gain? Gain is the action you need to do in order to correct for deviation, right? But don't stress it. We will unpack this down the line, right? And then you now apply these control outputs. You apply the control outputs to your process, and then you have your control being done, right? So again, error equals to set point minus measured value. And then your control output, how do you determine your control outputs? So your output plus gain times the error, right? By the time we will unpack this gain, right, that is where our controller actually comes in, right? And then look at the speed control function block. How many people knows what this KP means?
Proportional control.
Proportional constants.
Yeah. Proportional controller, proportional constants. So that's this KP is simply defined by the equation y equals to mx plus c. For every increase, for every unit increase in x, there is a corresponding unit increase in y. So that graph displays a straight line, right? So this is the pseudocode for a function block. You have var input, you set the speed, and you have the actual speed. And then you have your proportional control, right? You define your terms, and then your output will be your speed command, right? And then your speed command will be the cumulation of speed command plus the proportional control times the set speed minus the actual speed. So if you look at all of this, right, and you come back here and you look at this, you'll be able to correlate them and say that they are the same thing. This shape here, this symbol here shows that you are acting on the existing speed command. So whatever you have here, you are adding it to this speed command, whether you add or you subtract from it. So here, the set speed is your set point, right? The actual speed is the one you measured, right? And then look at these brackets, set speed minus actual speed. You now multiply it by this KP by a factor, right? And then you add that to your existing speed command. So at the end of the day, you begin to realize that control is actually understanding. All of this we have done, this is a program you will write. This is what you are trying to code on the PLC in order to attain control. Just like you have KP here, which is the most basic and simple of all the controller types, you can have KP plus K high, which is proportional and integral, right? So, but this is just an illustration for you. And function block at the end of the day is that this equation or this code will have been written and bundled together such that when you get to whether Studio 5000 or TIA Portal, you just pick it. You just pick this code as a symbol, maybe like a rectangle. You pick it and then you configure all the various parts of it. You configure the set speed. You point this actual speed to some kind of sensor somewhere so that it will take that as the value of the actual speed. And then you configure your KP. You tune it. That is where tuning comes in. So look at it. Set speed given by the human, actual speed detected from the process, KP given by mathematics. That is a control algorithm. And then you do you define your outputs, right? And then this is the what is inside the output. You can see speed command. That is what we're using as the output. The input, we define it, we define the output, and then the maths that give us the output. Is it clear? I want a feedback on that. It's important we understand this.
How do we determine the speed command?
How do you determine the speed command?
Yes.
That is the output, right?
Yes.
So from here, now, this is the equation for the speed command. Can you see where my mouse is?
Yes.
So the speed command is speed command plus KP times set speed minus actual speed. This term in the bracket essentially is what we call the error, right? The speed command, there will be an initial value, right? Once you start the system, right, in a real system now, once you start the system, there will be a reference speed that the system will just assume, or let's call it a default speed. Now, as the process continues, the process will now, and then you have set your own, the speed you want this system to attain. Sorry. The speed you want the system to attain, you have set it in the system. So it's somewhere in the memory. This actual speed, you have pointed it to some kind of sensor, maybe an encoder, right? So the system is continuously reading the value of the encoder. And then, so it takes the value, your set speed, and subtract it from the value of the encoder. So this value inside this bracket could either be minus or plus. So whatever that value is, it multiplies it by this KP and then add it to the existing speed command, the default speed command. So that gives it that speed command at that time. And then the process go through the program goes through the scan again, right? It scans continuously and continuously updates this speed command. So if your scan time is, let's say, 5 milliseconds, then this speed command will be updated every 5 milliseconds. Does it make sense to you?
Yes, it does.
Okay, great. So this logic is vendor neutral. Whether it's Siemens, it's Rockwell, or Schneider, it is the same idea, but different syntax. And I'm going to illustrate that also in the course of this series. So, I mean, this is what you have in your level, ladder logic. So your level set point is subtracted from your level process variable. And then you add it to your gain, and then you have your valve out signal, right? That's essentially, I deliberately tried to avoid, I mean, this is the introduction. So I tried to avoid anything OEM related. Let's be neutral for now. Let's understand it in terms of our normal addition and subtraction. Right. When we move into the control theory, that is when we now begin. So it is this gain. How do we calculate this gain? That is when we'll now be using our differential equations, our calculus. So all those mathematics are just tools to get as accurate as possible as this game. Right? So why control feels like black magic? It is because sensors drift, actuators saturate, and then processes lie. And then engineers, they tune blindly. Oftentimes we approach tuning like we are trying to turn on up or off the volume of our radio. Right? That's how we approach tuning sometimes. We don't, and that is not going to how would I put it now? I mean, that's not going to yield a decent result. So control exposes all of it. So again, once you understand, once you have an understanding of this, and I will share this as soon as possible, probably by tomorrow, you'll have this. Just go and look at this. In fact, look at it from here. Right? Look at it from here. This core idea. Let's lock that in. Once you lock that in, you will see that everything we build on this will be very, very, will be very, very relatable. So try to understand this. If you don't understand this, drop your questions in the WhatsApp group, and then we'll explain more so that if all of us have a base knowledge of this, understanding of this, it's going to make our jobs, it's going to make our learning very easy. All right. So control doesn't create problems. It reveals problems that were already there. So, I've seen a lot of frustrations, right? In the field from operators, it's this control system is just causing problems, this and that and that and that and that, But those problems existed, right? And then your lack of knowledge of the system is what is causing you all the confusion. I was in a plant just last week, right? Somewhere in the north. And I needed to get data out of S7 300 PLC over Ethernet. And I needed to get that data out and deliver it to get that data out, convert it into IEC 104 protocol. It's a power systems, power SCADA, and then deliver it into a remote SCADA system. Right. I didn't want to use, because of the industrial computer we're using for this and because of the cybersecurity requirements, couldn't use very big and heavy applications. Because of the fundamental understanding of how these things work, right? It was a script that I wrote to address all the data blocks in the PLC. extract the data, format it, format it according to the 104. What's it called now? The 104 ISO 104 protocol. And maybe if there is time before we finish, I will just show you the codes briefly. Okay. So why control switch like black magic? And then one of the takeaway for today, I want you to think on this. These are the questions engineers ask on site, not equations. Conveyor load increases suddenly. What changes first? So look at this and look at the impact. So if you increase your conveyor load suddenly, what changes first? Right? Think about it. We'll discuss it in the next class. Separator inflow spikes. Which variable reacts fastest? Then which loop would you tune first? So I just want you to think about this and identify the problems. You don't have to solve it. You don't have to break your head about analyzing, doing mathematics and all of those things. But think through it and identify the problem. The priority problem, the second priority, the third priority, and then we can discuss it. In actual fact, we can actually discuss it on the group, before the next so that will save us time. So impact on operations, benefits of feedback control systems, product quality, reduced downtime, and then enhanced safety. So I've given you something to think about, right? About the conveyor and about the separator, and so think about it, and let's have that discussion in the WhatsApp group, and let's take it from there. And just in summary, the key reason for feedback control, because we want predictable results, we want to avoid manual intervention, we want disturbance compensation, and then we want simplified processes. So thank you. At this point, we'll go into questions and clarifications. So as I mentioned earlier, there's going to be a training for up to 20 persons, and the cost is going to be 30,000 naira. And if you're interested in it, reach out to Oraolua. Notify Oraolua, and she'll give you more information. This series, I will try to follow this through every 2 weeks, on weekends that I can manage it, then we'll probably take some, lessons. Of course, everything will be recorded, and you'll have the recordings so that we can quickly build this foundation and then move on to other things. So thank you very, very much for listening. So if you have any question, let's get to it. Any question?
Good morning, sir. So I have a
Good morning. Okay.
when you were discussing about open loop and closed loop systems, and you explained that open loop has no feedback, I'd like to quickly ask you that are there systems or are there any systems where open loop is more preferred to closed loop systems, or always closed loop over open loop?
So again, it's a design issue, a design question, right? There are some systems where you can utilize open loop. For example, all you need, so you know, in a plant, you can have series of processes, right? I mean, so you can run maybe like 4 or 5 processes. So for example, now you are required to, using the soap manufacturing example, for example, you are required to deliver water at a minimum of 30 degrees Celsius into the vessel where you are going to mix the caustic soda, the perfume, right? So you have another vessel to raise the temperature of the water. Now, the process requirement is that the water should be at a minimum of 30 degrees. It could be 100 degrees, it could be 150 degrees, it could be superheated, right? So the question now is, you can just eat it up. I mean, you don't need to put any control system on that. Because whether it's 30 or 40 or 50 or 60 degrees, the process will take it. But the question now comes when your plant manager or plant management now says that we need to optimize, you are using too much energy. Since the process only needs 30 degrees, a minimum of 30 degrees, if you heat that water to 50 degrees, you have wasted energy between 30 and 60 degrees, which means that you have wasted money. So you can now decide that, okay, the cost of putting a control system in this, implement a feedback control on this water heating process, and the cost of energy, which one? And you weigh the two together, you can now decide, okay, let me just leave it open loop, or let me just put some sensors and a controller. The cost will pay for itself, maybe within a few months or 1 year. So that's how you make those decisions. So you can run some systems as open loop if you want.
Okay, thank you so much, sir.
Yeah. Any other question?
Hello?
Okay.
Hello?
Sorry, can I speak?
Please, can I ask a question?
Yeah, sure.
Okay. Could you just go over that part of in the control algorithm when you are talking about the scan time? Could you just go over like what you mean? So it's like you've been able to design your algorithm. So how does it relate with the scan time? Is it the scan time of the PLC or something?
So the scan time. So when you all of this, right? Can you see my screen?
Yes, I can see it. I can see it. Yeah.
Okay, this is the slide you were referring to, right?
Yes. Yes.
Okay, now, so all of this, everything written here, resides in the controller, PLC or whatever. So all of this code. So this is essentially going to be translated into a code, and it resides in the controller, right? The controller will start from line 1 of your code and run to line maybe 100, right? The time it takes the controller to run through all of those is the scan time, right? So if you convert this into, let's say, ladder logic, and you have, let's say, 100 lines, 100 rungs of ladder logic, the controller will start from rung 0 on the left, scan to this, get the output, go to rung 1, scan to this, get the output, go to rung 2, and then as it is scanning, it is updating all the internal registers with values, so that by the time it gets to rung 100, it goes back again. If value here, if level PV changes, right, it has gone through this, it has updated this register, and then it is on wrong 50, and then level PV suddenly changes, that is not going to have effect until it finishes this scan and then go back again.
Okay.
Yeah, so that's how it happens.
Okay. So it has to be like a complete cycle of before it gets to
Yes, it has to be, yeah. So it updates value once every scan time.
Okay.
Yeah. Right.
Yeah,
Any other question?
Hello, can you hear me?
Yes.
Okay. Please, I want to ask, maybe there is level to maybe sophistication of this control system, especially when you are trying to control two outputs for a single process. For instance, now maybe the time the time it takes to form a bottle is supposed to be set at 2 seconds. But we know that the input variable for those particular bottles to be formed depend on the temperature, the heating of the plastic that forms the bottle and the pressure applied. So now if maybe it's taking more than 2 seconds, then I know that I need to control the temperature and maybe the pressure. So do we have some kind of control block that actually knows which one to use to control the process, either temperature or pressure, and depending like algorithm to know which one to prioritize in that kind of situation?
Oh, okay. So I'm trying to see how to answer that question. So you have two parameters. Okay, I don't fully understand. Can you come again? Can you come again, please?
I have two parameters that determine
Okay.
of my
Okay. So you have two parameters.
Yes.
Okay.
But now it's not all the time that to control both. Sometimes it's only the temperature that maybe it leads to the control. Sometimes it's pressure. But both actually the output of the process. I don't know, maybe if there are more sophisticated algorithms in terms of which to know which to use to control this, and maybe both needed at the same time to control the process.
Unfortunately, I didn't hear you very well, but I think I get what you're trying to ask. So for every process, right, there is something called the control philosophy, right? If you want to form a bottle, for example, temperature is a factor. I'm not familiar with bottle forming, right? But I know temperature is a factor, and then maybe you have a time expectation. Honestly, so can you send it as a message? Can you send it? Just type it in the comment box. Let me understand your context, or if you can drop it in the WhatsApp group. If that's okay. Hello? Hello? Can anybody hear me?
Yes, sir. Can hear you, sir.
Okay. Yeah. So if you can drop that question in the WhatsApp group, it will be great. I cannot.
Okay.
I mean, I don't understand it here. Any other question before we conclude?
Yeah, hello, sir. I
Yes, sir.
also have a question. Morning, everyone, and thank you for the session so far. So mine is more like a question slash plea, babe.
Questions like what?
Plea rather. So I It's more of the
Yeah,
process.
you
Hello,
said
sir.
questions like what?
Uh-huh. And most of the process, most of the examples you've been given when you're making
You are
your
breaking off. Oh,
yeah, a call. Sorry, sir, a call keeps coming in.
okay.
So, like I said, most of the examples you've been given, they
Yeah.
are more process related. Maybe if you want to, maybe in the wellhead or manufacturing. I just wanted to ask, in a plant where they are generating their own captive power, where
Right.
we have gas turbines for the utilities, and maybe they are going to have like a heat recovery steam generator. I know there is a level of control that is also involved in that, and
Yeah.
I don't know if we could also cite those kind of examples or even discuss it separately if it's something that's dense and complex, because I know there are scenarios where maybe a backup maybe one of the feeders is down and a backup generator needs to come online automatically. There's some control involved in that. So I just want to plead if you could also include this in the delivery of the presentation as well, so we can see how the electrical engineering and utilities aspect comes into this control and automation discussions we have, rather than just the process
The
process.
process people.
Yeah.
Okay. Okay. I mean, that's understandable. Yeah, ironically, I was at an hydropower plant all through last week. So that's noted. We'll factor that into our case studies.
Thank you, sir.
You're welcome. Any other question? Okay. Okay, so in the absence of any other question, I think we can call it a day. Thank you for your time. Right. Thank you for your time, and we'll announce typically let me see. We should have another engagement by the 21st of February, right? We'll see how that goes, but just watch out for the next engagements on the WhatsApp group. So have a beautiful weekend. Bye.
Thank you, sir.
Oh, someone raised his hand. Is there a hand up? Okay.
I think it's just a thumbs up.
Oh, okay. 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 All right, guys. Bye.
Bye, sir.